So at this point, what we've done is we've developed a set of differential equations for this system. And we've also identified the idea that, in fact, the density of error is going to be really important. And we thought it would be important maybe at this point to think a little bit about what are the steps we're going to follow moving ahead, right? So we've kind of gone through the derivation stuff, but how do you sort of go from this derivation stuff to actually having something that works? So let me lay out what I sort of would think about. The first thing I would probably do is I would write the sort of shell of my density function and have that density function just pass back 1.2 kilograms per meter cubed, so that I sort of had a density function that I would be able to use in the future, but that also I just knew what it was doing. It was just passing back the constant. Right. With that density function, I would then go on and do something that would probably be an adaptation of the baseball problem that's from the diagnostic. I think we have an exercise that's around sort of simulating a baseball, and if you actually go through the math here, it's exactly the same math, right? So I should actually be able to use that code, reuse that code, and modify it a little bit so that it just calls this density function. I guess the next thing I would probably do is try with that code running a simulation of shooting something straight up in the air with the velocity that Jules Verne asks. And the reason I would do that is not to actually see if that would get out of the atmosphere, just so much as to find out what does happen if you assume constant air density.
And you could even at that point think of using a smaller V naught, since he talks about this very large one, but maybe something that makes sense to you.
Yeah, and I think actually I shouldn't have said the first thing I would have done would have been to run Jules Verne's V naught. The first thing I would have done actually would have been to probably set the cross-sectional area of the ball to 0, throw it in the air at 10 meters per second, and see what happened. And I would expect that it would follow a parabola that I would remember very well from AP Physics, with 1/2 AT squared kind of behavior, right? So I actually would know what the simulation ought to produce if I turned off drag, and I'd be able to show that it actually did reproduce that, right? And then at that point, I might turn on drag and say, okay, well now does it produce something that's more reasonable, where I kind of know where if I throw a baseball at 10 meters per second, what about should it do? And I could sort of look at that. I could simulate a balloon and see what a balloon would do. So sort of do a lot of kind of sanity checks where I'm changing parameters in order to make the solution, make the output be something I can predict by running the movie in my head, and then checking the simulation produces something consistent with the movie I'm running in my head.
Right, so what I'm hearing is that you're actually doing some things that are very different from Project One. You're not running out there and finding a graph from a research paper that you're just going to copy. You're actually thinking about it a lot from the mechanics intuition behind what you'd expect to see happen.
Yeah, that's right, and I think that it's probably the case that someone who was a professional person working with pharmacokinetics might actually be able to do some of those kinds of intuitive kinds of tests with the pharmacokinetic system. I think all of us have physical intuition about what happens if you try to throw a balloon across the room, and so I think appealing to physical intuition is much easier to do in this venue, but I think as you develop competence in any venue, you can often appeal to those types of intuitive tests. Right. But yeah, I do a lot of those types of sanity checks, and a key thing I think in those sanity checks is the idea of saying, I'm going to try this, I predict what will happen when I try this is X, and then run the simulation. Because it's really easy for me to fool myself. Like if I run the simulation first, I can come up with some cockamamie explanation for why the simulation produces the results it does. Whereas if I actually commit to something before I hit go on MATLAB, I'm much more likely to actually think critically about what the output is. Right? So I do those sanity checks and make sure I was actually pretty confident the thing was working.
Right, and there's a purpose, though. There's two purposes for these sanity checks. It's not just to make sure your code is right. It's to make sure your physical understanding of the system is right.
And it's actually in some ways, it's hard to distinguish between those two. Like certainly with the equations of motion, one of the things we did is sort of went through it and thought, okay, well, this force is opposite the velocity. That makes sense. As the velocity increases, this force increases. That makes sense. So that kind of making sure that your mathematical model is sensible is something you can kind of test with those kinds of thought experiments even before you write code. And then once you've written code, when you do those thought experiments, you're both testing the code and the mathematical model, and sometimes it's hard to know which one you're testing.
And your assumptions.
Yeah, and your assumptions, yeah.
But that's definitely helpful when then thinking about coming to check-ins or talking to ninjas around what's going on, my code isn't working. So making sure you're sort of separating out some of
Yeah, I mean, the extent to which people blame code when in fact it's usually that their physical model is wrong either from an assumptions perspective or the mathematical implementation of that physical model is wrong.
We all want to do it.
Happens all the time.
It's the easy.
Yeah, it's like,
it's always the code. Why not?
It's easy to blame MATLAB.
It's not you. It's great.
So I guess once I'd done that, then I would start to do the stuff that would actually be related to the investigation I was trying to do, right? So I really wouldn't actually start to think about Jules Verne at all until I'd made sure that I was pretty confident that my model worked in situations where I knew what the results should be. Right? And then at that point, I might do what I'd said earlier, first trying just let's keep the atmospheric density constant and see what happens, right? Then let's try making the atmospheric density very linearly and see what happens. I should be able to actually, based on my first result, I should be able to predict that my second result should go higher and shouldn't go crazily higher, right? Because I know that I'm still pushing through atmosphere for a good chunk of that flight, right? And I'm actually pushing through atmosphere at the time when I'm at my highest velocity, so the effective drag is going to be largest. And so I'd sort of go through multiple iterations of kind of playing with it and then making an improvement to the drag model, playing with it some more before I did anything. Like I wouldn't do anything like creating a p-color plot until I had run a whole bunch of simulations where I actually was producing a time series of like height versus time, and I could really explain what that height versus time graph looked like. And finally, once I got to that, then I would probably tweak things a little bit to say, okay, do I know about what my answer ought to be? Like what initial velocity is going to approximately get me into the atmosphere? And then I might start to think about, okay, is there some good way to communicate this result and show what the sensitivity is or something? And so maybe I would make a p-color plot. But honestly, for this one, I don't see what a good p-color plot would do. I think it would end up making things more confusing than anything else.
Any other thoughts?
So, I don't know, that's what I would do. Would you guys do anything differently? Does that sound about what your procedure would be?
Yeah.
I can't see you nodding, Allison.
True. I'm doing a lot of nodding here. I agree with all of this.
All right.
Good answer. Okay, I think we're going to wrap it there, guys. Or do you want to talk about the Canon thing?
Well, I guess one last thing is if you can start thinking about the Canon design, you can focus on, again, how you make things simpler. And I think that's sort of the lesson in all of this is how can you start simple, right? So we started with no Canon, and at some point we might think about what are some simple forces that we could use to replace the Canon.
So I'll tell you what, if we get enough likes on this YouTube video, we will make a Canon model. So you heard it here.